So what was my motivation? So our motivation was really to find a very simple model where we could test the ideas that that really came from this all this work on GG, GHD, and other Gs. I mean, many GGI, and we were also motivated by a paper by Pablo Ferrari and collaborators about soliton decomposition of the box ball system. And well, last motivation was to study a model which is a kind. I mean, that's what we discovered. It's a kind of model which is directly related both to TBA on one side, which is the kind of things condensed matter physicists know well, and solitonic physics. And this I will explain a little more in my talk. So what is the origin of the model? I mean, this is a totally Japanese model, I must say. So it came from something called cellular automata by so Takahashi is the famous Takahashi of the TBA, and Satsuma. And these people really, they had the idea. It's not the same. So I'm sorry. So I'm really sorry. I thought. So this Takahashi. So they had the idea of taking a KdV equation, and what they really did is did something which seems very strange to me. I mean, called ultra discretization. So the idea of ultra discretization is to replace whenever you have a product by maximum, and whenever you have a product by a sum, and whenever you have a sum by the maximum. And you have to be clever. I mean, it's not so trivial. You take the equation of KdV and you obtain this model as a kind of limit of this model. And then 10 years later, then this was the kind of rise of quantum groups. And quantum groups, then there was this idea of a crystal limit. And so Hatayama, Kuniba, and Takahashi understood that by taking the crystal limit of the XXZ chain, I mean, or maybe generalization of XXZ chain, they could recover this model. So crystal limit, I mean, for us, is really what we would call the Ising limit. I'll talk a little more about that. So when you have the XXZ chain, you have this parameter which you call delta, and when you let delta go to infinity, you recover this limit. So what is so we want to study a little more the hydrodynamic of BBS. So not understanding too well, you see what is BBS. You have a kind of Z array, and then you put balls at each site. So each site is either occupied or empty, and then there is a rule that makes you travel. But you see here we have oh, this is not very good because there should have been 3 balls on the first one. So you have 3, 2, 2 balls. No, 3. Well, I mean, that something is not good. Okay, let's forget about that. Oh, so that's better. Yes. So this one is better. So here you see you have 4 balls, 3 balls, and 1 ball, and then suddenly you let the system evolve in time. And what you see is that the 4 balls are ahead of the 3 balls and are ahead of the 1 balls. And we can think of this when they are far from each other as solitons. So these solitons evolve. Well, I will explain a little more about what. And the big solitons go faster, and they overpass the small solitons. So. So now I will explain the rule here. So what is the rule of the evolution? So this is what here I draw vertex. So it's really what I call a crystal vertex model. So you have a kind of well. So now what is the idea? You have 2 times here. You have t equal 1, say, and t equal 2. And here you have to imagine that you have partings, And the parkings, they can only accommodate one single car in this model. So either the parking is occupied or it's empty. And then there is a bus here that goes on the road through the parkings. And the bus driver, he has a very simple attitude. If the parking is filled, if the parking is filled, he picks up the ball. So this is supposed to represent the occupation of the bus here as he goes through the parking. So here he goes, he sees that there is a ball, so he just picks up the ball. So that's so then the parking is at time 2, the parking is empty. He sees another ball here, so he picks it up and it's again empty. And when it's empty, so he sees that the parking is empty, he gives a ball. So he has one ball. The parking is empty, he gives another ball. But here the parking is empty, so he would like to give a ball, but he cannot give a ball anymore. So this is kind of finished for him. So this is the very simple rule of the BBS. Now we can slightly generalize the model. Here I said that the bus was taking, but of course a bus does not have infinitely many places inside. So we define a model which we call L. And so if we take L, we said that the bus has a maximum charge, which is L. So that is to say, when he will have L balls inside, if he sees a full an occupied site, he will not be able to take the ball. So it's just the symmetric rule as when he was empty. So this defines, if you want. So this is really the idea of people who come from physics. It is really the idea of what we would call a vertex model. So A, which is between 1 and L, is on what we call the internal line. I mean, and on the physical line, you have the number of balls, which is 0 or 1. And you have a kind of conservation law, which tells you that A plus B is A prime plus B prime. So, in other words, when you will think of this model, this will be some kind of density. I mean, for example, if you know the models like TZEP, EZEP, or just the number of balls, the number of spin-ups is the density. And the number of balls that are here has the interpretation of a current. So it's nice to have a model where on the same picture you can see the density and the current. So this is called, yes, why is this called a crystal transfer matrix? What is, so it looks like a transfer matrix if you want, but it's not a matrix because in each column of the matrix, you have only one non-zero matrix element, and it's one. So this is what we would call a cellular automata. So I mean, coming back to yesterday's talk by Spohn, Herbert Spohn, it is really, you will see it's very similar, but yesterday this was a classical model and today it's a cellular automata. But in both models, in both cases, the ideas of generalized dynamics work very well. So I think when you have the idea of the model, I think this is essentially all what is important to understand. The rest is just techniques. So this I think I already said that you see maybe I did not. So now there is some combinatorics. The model, it looks very simple, but it's not so simple. For example, if you have this transfer matrix with L and you act with another transfer matrix the following time, which has a different value of L, you can commute them. They commute. So I will not here the reason why they commute. It comes from some combinatorics ID, which is called the combinatorial R matrix, if you want, or the so real R matrix come back from very, very long time in the past. And in that case, you can find the combinatorial R matrix that will ensure the of the transfer matrices. So that's already a kind of strange things about that model. So yes, sorry. Yes, maybe something which I will say here. So you have this idea of commuting R matrices, and then because of that also you have commuting quantities, which essentially are, if you so I introduced the idea of solitons at the beginning. The number of each kind of soliton is conserved independently. So you have an infinite set of quantities, which are the number of different solitons. So this is the connection with GG. If you want, we have an infinite set of conserved quantity in that model. So here I will just give a another description of the configurations, if you want, of the model in terms of Young diagram. So to a model, we can associate a Young diagram, if you want, as follows. The rows are the lengths of the solitons, and the number of rows are just the number of solitons which you have in the model. So, and in fact, these are all the conserved quantities of the model, the number of solitons of each kind. So we produce this quantity mk, if you want, of mk of eta, which is the number of solitons of type k. And then, well, when we will divide by the length of the system, mk divided by L will be our soliton densities, if you want. So now I wanted to show something more, so a little more about this soliton, because this is a bit where the mystery of the model comes from. So how will I describe the physics of the model? So I will have a kind of a Young tableau. So here, for example, it's not. So let's say 3. 2 and 2 like that. Okay, so this describes a configuration, if you want. So I have also the length of my chain, which I call L, which, for example, here I take L equal 10, 20. That's not very important. And so that's the soliton. So this means that I have. You mean big solitons? I am not sure. So this is so I'm not sure I understand. This means that in this model, I have a soliton of size 3, 2 solitons of size type 2, and 2 solitons of size 1. You don't know where they are located. So of course, if you let the system evolve a very long time on an infinite chain, they will separate. But you know for sure, maybe I don't know if I explained that, but there is a way to know where the solitons are. This I did not explain too well, but so that's the connection between the transfer matrix and the soliton. Imagine you have a certain configuration, and you act with the transfer matrix L. This very, and then you just count the number of zeros that are transformed into ones. So you look at the zeros and you look at, so this is not exactly the number of solitons, that's the energy L, but then there is a connection between number of solitons and energies. So there is a way to somehow exactly know where the solitons are by this procedure. Between the energies and the solitons?
The energies and the front between 0 and 1.
No. No, because I will explain. The conserved quantities are the energy. So here on this diagram, I want to explain a little better what the energies are. So the energies, I mean, so there are an infinite set of energy, which I will call epsilon k. And to know epsilon k, for example, epsilon 2, that's quite simple. You draw a line here at 2, okay? And you just count the number of boxes which you have left of this line. So for example, here in this model, I would have epsilon 1 equal 1, 2, 3, 4, 5. Epsilon 2 equals 3. No, epsilon 1, yes, is 5. Epsilon 2, sorry, is now 5 plus 3, 8. And epsilon 3 is 9. So you just count, and then all the epsilons, which are epsilon 3, and then epsilon k with k larger than 3 are all equal to 9. I mean, you don't really see sorry, this. No, they are the eigenvalues of the discrete transfer. Well, eigenvalues, quote unquote, of the discrete transfer matrix. So number of zeros transformed into 1, if you want. There is no Hamiltonian here, just a cellular automata. And then this is really the very non-trivial part, which I will not explain you, and this is a bit like what Herbert said yesterday. You can define another thing, which is the density of hole. And so the density of hole will be essentially, well, once you, well, I mean, it will be L. So this is not the density, but you can define pk, so associate, which is the length of the chain minus twice the energy k. And this I will, well, once, I mean, this is macroscopic if you want. No, that's, I should call this EK. So, and then I define I mean, if I divide by L, I will have sigma K. So I prefer to work with is 1 minus twice epsilon K. So that's really the crucial formula, which tells you what the density of hole is associated to a certain density of solitons. So we will have kind of two densities that play a role in the game, the density of solitons and the density of hole. And then I will explain you for, well, I mean, yes, here I can already explain it a little. Then if you have a certain number of solitons on your chain, you can ask yourself, what is the degeneracy of well, how many states on my chain can I construct with this density? And yes, these are capital, sorry, yes. These are capital E's. And then, so this, I am sorry, I can't, because this really comes from complicated mathematics. But I know there are two ways to understand this. Either you are a physicist and you come from quantum mechanics and you have done your TBA with the XXZ chain, and then you let delta goes to infinity, and then you try to follow by continuity the degeneracy which Bethe gave you in his chain many years ago. Or you are a mathematician and you really try to understand the degeneracy from scratch. And the degeneracy is essentially a product of binomial coefficients, which are just like that. I mean, it's the product over k of the number of I don't know how I would call this, mk plus pk mk. So it's the product of the, if you know, the sum of the hole and the particle densities, and well, the normal. I mean, here I could be mk or pk. I mean, that's not really. So it's just a product of binomial. And if you, I mean, if you have some experience with Bethe and that's typically the kind of formula which one obtains in the chain. So essentially, that's the. You see, it's complicated, but that's the only mathematics I will need to study this model, this degeneracy. J'ai pas compris. Tu peux reposer ta question? There is L, but this does not depend on L. Yes. This is for any L. This is independent of L. So that's what I gave. I think I gave the formula. No, I didn't give the formula. So sorry. So then I should explain the formula. I said that pk was L. Yes. So I did not give the formula. Minus twice the minimum of, so P, so sum, there is a sum over K of minimum of J, so JK MK. Sorry, so PK. So I mean, so this sum over K. So no, this sum over J. I mean here. So I fix K, I sum over J. I take the minimum of JK and multiply by MK. So this, I don't know. I didn't give the formula. So this is, I mean, if you think a little, this is this energy epsilon K, which I defined here. So epsilon K is this minimum sum. I mean, sum of minimum. So that's just the number of rows which have left. And so that's the formula for the pK. So I think now it's clear. So now let's go on a little further. So okay, I think I explained it. So this is the density. So that's so I will often use this big matrix M Ij, which is just twice the minimum of I and J. So whenever you see this matrix, you just imagine it's twice the minimum of J and K. And then so we want to do something called thermodynamics. So thermodynamics is just assuming we let the size of the chain become very large. And so we have this sigma J. Oh, yes, thermodynamics. Yes. So sigma J, which is just pK renormalized by L. And as I told you, now this becomes rho K plus sigma K rho K. So that's the product of binomials. And then we have our energies. We can put, so that's really ideas of GG. We took how it's called, fugacities, beta K associated to all this energy. We take the product and we want to minimize. So we have to do the sum of our all the tableaus and try to compute this. So this is what physicists know very well how to do. So I just explain just in a short transparency. We define the log of Z. We define this as being the free energy, and then we minimize it with respect to rho, for example, to each of the density, and we end up with this minimization problem. And what is very nice is that this minimization problem introduced some quantities, which is the ratio of sigma over rho. And I mean, well, I mean that's an old thing did by Yang and Yang many years ago. And well, that's kind of one way to present the equations that come out of this is so-called the Y system. So you have to solve for this Y system. So each of these Yi's has to obey some kind of, you see, it's kind of discrete equation. And the free energy, I have put the free energy because it looks very much, it reminds of a free no, not a free, of a fermionic system. I mean, it's log of 1 plus E minus beta times the energy. So although it's a classical system, well, I mean, it has some kind of a fermionic structure. Well, I mean, again, so we are not going to now the model we are going to study, we are not able really to put as many beta Ks as we want, but we are going to concentrate on what is called IID model. So that is to say, we are going to put with some probability Z divided by 1 over Z at each side of the lattice, a ball. So we are going to drop balls. And so now the fact that this fugacity is not, I mean, fugacity, the number of volts you see is the total number of boxes in your diagram. So this is the infinite energy. So we put a fugacity Z to the infinite energy, and then we do this minimization. So this we can do because there is a kind of trick. Well, here I just wrote the TBA equation just in a way that physicists understand better, but it's just the same TBA equation as before. But you have this kernel, which is 1 minus m minus 1. So just remember, I think yesterday you showed 1 minus, you showed the same kernel, but in that case, in our case, it's m the. So yes, well, the trick which enables you to do this is that you have a sort of change. I mean, you just define square root of 1 plus yi, you call this q, and you write exactly the same equation as before, and you discover that it takes this nice form, and then people love it because they recognize that this is some kind of Schur function identities. So the Q, in fact, they are a very simple Schur function in that model. So the point is that now, because of this, we can have in this model very explicitly as a function of Az, all the densities rho k and all the sigma k. We have a very explicit expression in terms of Z. We could add a second fugacity for the one soliton, but not much more. Unfortunately, we are not able to write rho k and sigma k as function of all the betas. Yes?
So why this does not depend on this L?
Yeah, that's a good point. It does not. Well, I mean, before I explained sigma and rho, and nothing was depending on L, on these quantities, if you remember. The rho and the sigma, they are independent of L. You see, you have commuting transfer matrices. So these are conserved quantities which are, well, these are quantities which are kind of not associated because they commute. Imagine you have some kind of spectral parameter. L is some, I mean, it's not really a spectral parameter, but it's something which which introduces. So it's not in this quantity that Now I want to somehow connect. Sorry. Yes, I would like to connect this model now to something more physical, because I introduced this matrix M, which was minimum of I and J. And now I would like to show you that although it's not you can somehow see it in the solitonic process. And then I just show you a kind of a cartoon of what's happening. So let us just look at the motion of 3 solitons. By the way, how much time? Il faut que je m'arrête à quelle heure? I still have half an hour. Okay. So imagine we have the motion of 2 solitons and 1. So we have a kind of so we have 2 solitons here, and they are behind here. And I have a 1 soliton here. And then so I make my motion. So maybe you have already seen that 2 solitons, they want to travel. So this is take L large enough so that there is no problem. I mean, if I take L equal 1, for example, the simplest model is just a uniform translation of my system at speed 1. But here I take a large L, so 2 solitons move at speed 2. This one here, so this one has moved once. I do it a second time. So a second time now it's a little more. So if L is very large, you can just think of the motion like that. This one passes over this one, so it will be here. This one has now to pass over 2, so it will be here. And the last one will pass here, so it's here. So now I have some kind of picture like that. So the 2 soliton has passed the 1 soliton. But now, I mean, there is something that has occurred. And the occur is that rich people become richer and poor people become poorer. So what does that mean? That means that the poor 1 soliton has been slightly slowed down, because normally his normal position would have been here, I think. And the 2 solitons, on the other hand, have been accelerated because the normal solution position would have been here. So let's see how much. So you see the one soliton has lost. So we can introduce this quantity delta. The last soliton has lost -2 compared to what his position should have been if he had not encountered the big soliton. And so delta 2, and the big soliton has gained 2. So what does this 2 mean? In fact, well, that's again this matrix Mij, which I introduced. So the shift delta is Mij, twice the minimum of Ing. So there is a kind of, I mean, this is really this GG thing, I would say. Yes, not GG, GHD thing. That there is a big connection between the scattering matrix. This is really the scattering matrix, if you want, and the formula for the degeneracies. So okay. So this I say in Word, but it should be more explained. But I don't have. So now that we have this shift, so there is this beautiful equation which I think well, it's very well known, but I cannot resist presenting it once more. And it's just telling you that the speed of the soliton in the medium. So very intuitively, you say that the speed of the soliton in the is just the bare speed. So the speed plus, I mean, the number of soliton of type P, which you have crossed per unit of time, times the relative shift. Because I mean, since you meet other solitons, you get shifted, so you get either accelerated or slowed down by the others. So so the formula is so this is this delta. So the formula is just this. So it's just a linear relation which relates the speed to this. Okay. So it's intuitively it's well, I mean, it's a simple formula, but really to understand clearly, it's hard work. So I think it was proved in the first paper, which I mentioned, the paper in that case. And so now there is this other formula, which I so I mean, the GHD formula you can get from TBA, but in that case, I think you just need to think of this formula and you try to solve now. It's a linear equation for the speed, and then you're naturally led to introduce. Well, I mean, there is some kind of gauge freedom. I mean, you're not obliged to take this matrix, and you could and Y. I mean, so people usually would not use M and Y, but just solving this. And you realize that so you define this kind of dressing operation where you take 1 plus my minus 1 multiplied by a, and solving this equation, you realize that the speed of your soliton. So this time it depends on L. So you have this dressing operator divided by 1 dress. So yes, so I did not explain why. Maybe something I did not say. What depends on L? Even when the solitons are alone, is the maximal speed of the soliton. Because you see this carrier, he has a maximal charge L. So when you have L, the kind of bare velocity of the soliton is bounded by this number L. It cannot go beyond L. And so when you solve the equation for the effective speed, you have to take this into account. So now the effective speed depends on L. And I must say, in the numerics, this is like exactly as amazing as, for example, in Bethe-Ansatz, you have this Sutherland equation. So Sutherland discovered a kind of what he calls asymptotic Bethe-Ansatz, which is true for when the density is extremely low, but then is valid when the density is extremely big. And in that case, I mean, this bare velocity can be of the order of 3 or 4. And when you put the solitons in a medium, the bare velocity can grow like 30 or 40, and still the equation is valid. So it's a very strong equation. I mean, when it was, I mean, I think Zakharov did not really trust it, so he had a kind of introduction of kind of, well, in another context, perturbative way, but then recently, I mean, all the recent work about it realized this is an exact equation. So here now, I would like just to present the essential equation of this GHD, if you want, which we need to use. So there, I mean, all of the equations are intuitive, but maybe they are not so trivial. One of the equations is what is the current now. So I told you the current is the number of carriers which you have. So you say, okay, I do hydrodynamics. The current is, well, there are many, you can associate currents to any conserved quantity. So here I associate it to the density of hole, but I could replace it by the density. So the case soliton current is just the density times their speed. So that's a very natural equation. And then you have this quite non-trivial equation that it conserved, it's a conserved equation. That is to say the density, I mean, so this is a fundamental equation, which of course follows from that. Another equation, which is this, I would call this really comes from GHD, is that you can make, so if you, this is dt sigma plus dx sigma v, I mean, j sigma v. So sigma and v are together, but you can take the v out of the sigma. And so you can write, so this y, they obey this. So this is, I would say, more physically more, so this is kind of Riemann equation, if you want, because now these y are called normal modes, and you can use the method of characteristic to say that things move at a speed v to solve this equation. So in a way, this is more intuitive than this equation if you want to follow the motion. I'll explain you how to use it. And then the last thing, which came really from Yang and Yang, and also which is a kind of very striking thing, is that this y. So Yang and Yang, they looked at the minimal of the free energy, but then they looked at the oscillation, the normal modes, or the oscillation of this free energy. So essentially computing the correlation function of these quantities, and they observed that it was a diagonal. So and this is very useful. So log of y is epsilon, and that these epsilon are diagonal. And if you just repeat the Yang and Yang calculation, you obtain an explicit expression for this correlator. And in the transport, and I'll talk about transport a bit later, that's essential to be able to do some calculation in transport. So now normal modes current. So now some simulation just to show you. So what we do here, forget about the top because, well, it's kind of symmetric. We feel, so that's the typical Riemann experiment. In that case, you put solitons on the left of your system, vacuum, nothing on the right with certain density. So here we change the density, and we look at the evolution of the system, and we see this plateau that develop. You see, well, they are nearly, sorry. Well, I don't know in which direction I go here. So okay, so here you see that there are plateaus that develop. So the plateau, they are not very hard to imagine to understand, because then you have in the left you have many solitons, so they have all their densities, but one of the soliton is slightly slower than the others. So this soliton after some speed, these are rays. I mean, by the way, these plateaus, they are drawn as a function of r over t. So you can see a certain ray, I mean, at the speed of this slow soliton, and then it just disappears from the picture. And then following from the equation, all the y's are conserved, so you don't have to solve to border. But you have to solve back for the equation for the speed, because the speed are function of the y's. And so you solve for them, and then you find the second ray and second soliton disappear. So you see this plateau structure, which tells you how fast the soliton disappear from your thing. So that you can do, and you can make an analytical prediction. And so you see the dotted lines are the analytical prediction, and this is the simulation, and it's perfect. You can very perfectly predict analysis the places, so the velocity at which the plateau occur, and also the height of the plateau. So that's something which is nice. And something now which I wanted to say is you also can see some kind of slight enlargement of the thing. So this was explained by people by Denardis and Golakap priest or whatever. I mean, so I mean, in fact, there is some kind of diffusion effect. So I took the picture from due to the fact that solitons collide together. So its motion is not strictly straight; it's slightly enlarged, and you can also make predictions about the enlargement. So instead of having a step, you have how is it called? Earth, some kind of Earth function with the width, which you can compute analytically, and that works. That works very nice. So we get perfectly good diffusion corrections in this model. I don't think I want to insist too much on these formulas. They are there. They are what they are. Okay, and so this is the prediction. So this is the prediction, if you want, of what is seen analytically and what is computed, what is seen on the computer simulation and the analytic computation, and essentially it's impossible to see the difference. So maybe in the last few minutes, I will now discuss a bit more the transport properties. So I must say I was a little disappointed because we worked hard, and then we realized that most of what we say, we could have just taken this paper, Doyon Spawn, and just play a little around with the formula, and everything would have come out just a change of so just this means that the formalism is very strong. I mean, it resists many models. The same formalism can apply to many models. So we considered well, I mean, among others, we considered the 3 quantities. So this one is trivial. It's just the density correlation function, the charge density function. So since the charge is conserved, it can be easily conserved. It's P1 minus P. And in terms of the densities, it takes this form: rho, sigma, rho plus sigma, Vi. So this is the infinite. So this is sum over all the speeds. And you see this Vi infinity squared. So more interesting is the second cumulant. So, well, why is it called second cumulant? Because you make a, well, I will talk, you will compute the large deviation function. So you compute the current that goes through, passes through 0 at time t, and then you compute the second cumulant. But I mean, playing around, it is also related to the commutation of J of 0 with the charge. So it's not P1 over P this time. I don't know why I put this P1 over, I mean, each time I put P1 over P, it's not true anymore. It's only true for this quantity. And then it takes a very similar expression, but now you have to multiply by this VI, the speed of the soliton I in the sum. I mean, okay. And the last thing is maybe the last a bit more, slightly more surprising things. It's called the Drude weight, which is, so big J is just, now it's integrated current over space. So integrate the current over the space and you compute its correlation function at time 0 and at time t. And it's, it's nearly always the same formula, except that you have here VIL and here you have VIL squared. I find it striking. I mean, you get nearly all the time the same expression, and well, okay. Then so this is the expression of the Drude weight for different values of L. So it changes drastically with L, and especially with L equal to infinity. It's kind of explodes as a function of this probability P. When you go towards 0.5. So maybe, I mean, there is obviously a kind of phase transition occurring at 0.5, which we did not, some kind of, you create a huge soliton if you want. So there is a kind of strange thing, and it's difficult to go, it's impossible to go beyond this value z equal 1. So okay, so that's the Drude weight. And what? Ah, yes. Well, I mean, just to say maybe something which is not in the paper by Herbert and Doyon is this. So in fact you can, because you have many energies and many times, you can somehow construct something which is a current associated to a certain time and to a certain energy. So you have two, if you want, you have two indices, the index for the time and the index for the energy, and then you get a very symmetric expression. So this is some kind of a generalized expression, if you want, which for these quantities, and it's very symmetric in the speeds. And what I wanted to say here, I mean, you don't need really to understand this picture, but this means that even microscopically, all these currents can be defined. So the fact that you have two different transfer matrices, one which is associated to the time, if you want, and one which is associated to the conserved quantity you're interested in. And by playing around, you can define, so the red things are the currents, the microscopic expression of the current. So these currents, they really mean and here, this is the correlation functions of this current. So they have a kind of microscopic interpretation. And so, but we tried to test this formula. And for small values of L, it does not work. So it doesn't work perfect. I mean, works not, no. So something is wrong with this formula. One of the possible reasons, I think, is that there are more conserved quantities when you go to small l. I mean, the kind of conserved quantities associated to the solitons are not sufficient. So maybe I did not explain, but the way to compute this is to use a trick, some technique called hydrodynamic projection. So you just insert all the conserved quantities which you have. I mean, assuming that you have a complete set, and you just use the fact that they are conserved to say that nothing evolves in time with that, and that's the technical tool used to compute this correlation function. So maybe there are more conserved quantities which we miss. I mean, that's a possible explanation. I don't know. Finally, just to say about something which was not in the old paper, but in your paper, but which is very, very easy to compute. So I won't be very proud about that, but you can compute the large deviation function. So the large deviation function is just computing what is the amount of current that passes through the origin in that model. Assuming, you see, it's a cellular automata. So all I mean, this was like what you what you would know who discussed it. Now I forget his name. Your younger student, former student who works with you and Doyon. I mean, I'm sorry, I forget his name. No, I just said the. Okay, so just, I mean, just to say, there is no. I mean, the evolution is completely deterministic. All the randomness is in the initial state. So that was, I mean, I wanted to mention Sakato talk because of that. So it's the same in this kind of problem. But still, you get you can still define this kind of large deviation function, and so in that case, just, I mean, I draw a cartoon about what happens, but it's supposed to be the difference. I mean, the current that goes through is the difference of the charge that you had at the origin at that time t. But you can really see that all the charge that is right has absolutely no role, because the soliton, they just move to the right, and all the charge that is here plays no role, because the soliton they will move here. So essentially, the only charge that is important is the charge which is here, and then you really realize that the thing which you have to do is some kind of renormalization of your coupling constant beta by this lambda. So it becomes again a kind of a very static computation. If you are, I mean, we were able to. I showed you were able to compute it's very easy to compute this current at time 0, and you compute this, and then you obtain a very simple expression for this large deviation function. So here I show this expression for L for general fine. I mean, if you take L equal 1, it's just the large deviation function of tossing a coin. I mean, if you toss a coin, you can compute the large deviation function, and that's essentially how it simplifies. And you can compute, well, in the rate function, in the case L goes to infinity. So this is typical of what a rate function. It's a convex function which reaches 0 at the expectation value of the current. So nothing really, except maybe that when you go to this z equal 1/2, z equal 1, sorry, you see that some kind of limit behavior. Okay. Okay. You have described a simple integral deterministic model, which gives kind of amazing agreement with hydrodynamical predictions. So that's one thing. Some things which I did not really discuss, but for example, this was slightly discussed in Matteo's talk. And also in the talk of this morning, there are some interesting combinatorics behind this model, which, for example, it's obviously related to Sechten's row bumping algorithm, and I think this is a good one. This is interesting for future work. I mean, so there are also other more complicated models. The balls could be colored, and many things, many unexpected things can be studied. So maybe some much richer physics can be extracted from this model than the one we extracted up to now. Okay, thank you very much.
Questions?
I'm wondering if the diffusive correction is related to the value of L.
Yes, I think the formula I showed were related to the formula of L.
So I guess if L is infinity, maybe this correction is vanishing, right? Or is it?
Right now, I don't. I think there are divergences with L goes to infinity, and Z goes to 1. I mean, this is really. Maybe we could go back, but I don't remember. So this is this formula. So what happens when L goes to infinity? So this Z is less than 1 in R. So if you let L go to infinity with Z, all the terms which contain some L, they go away. But okay, but of course, if Z goes to 1, then there is some divergence which comes from this term here.
So which means that if L goes to 1, it's like
L goes to 1. There is no diffusion because
there's no diffusion. Okay.
everybody travels.
Even at the same speed.
So
Yeah, okay.
Nothing happens.
Other questions?
Okay, so there was one thing which was a little bit too fast for me. I mean, the kind of states which you are looking at initially, I mean, they are GGEs constructed from the lowest order. I mean, like thermal GGEs. Is that right? Or are you,
sorry,
I mean, the initial state which you're looking at. I mean, let's say in your.
Oh yes, it's IID, just IID.
Okay, so this.
Course, yes.
Okay.
We could try to put, of course. I mean, the next thing we should try to do is to put some kind of fluctuating. Well, I mean, we did this two-step thing.
No, I mean the two-step is okay. I mean, I just wondered. So in terms of GGE, it's really the GGE constructed from
just
the lowest,
one
from the lowest conserved quantity. I mean, you did
we
not
could
try
put,
to do for sort of higher conserved. I mean, maybe starting to simulate what the GGE is. This might be complicated. I mean, so
analytically we can do two.
Two, you can do it. Okay.
First, but that's for the moment.
Density energy, so to speak, right? I mean, yeah. Okay.
Okay. More questions? All right, so if there are no more questions, let's thank the speaker again.